All right, we have come to that stage in our understanding of equilibrium and our understanding of acids to now start talking about weak acids, what that means for the pH and the Ka. Now we're going to need a couple of tools in order to make use of this. You don't need to write down this list of tools. Sorry if you already started writing this down. You don't need to write them down. I just want you to be reminded that these are the things that we're going to be making use of. Weak acids with the equilibrium expression, knowing what a weak acid does. Equilibrium expressions themselves was with the products on top, reactants on the bottom, where the balancing numbers become exponents. Here's the good news. With weak acids, or weak bases for that matter, because we're only ever talking about a Bronsted acid or base, movement of one proton, our equilibrium expressions are actually quite brief, and plus water gets left out because water is a liquid. We need to know how to work with pH, and we need to know how to work from how to find concentration of hydronium from pH. And then ice tables, we're going to shorten them up or tweak them a little bit this time because, again, everything gets fairly simple. Okay, there's two kinds of questions. Number one is you can calculate the equilibrium constant, Ka. The other is find equilibrium concentrations. Now for weak acids, it's going to look a little bit different simply because of the information that we have or how we can get that information out. So what I'm going to do is I'm going to give you a question, we're going to work through the answer in detail, and then at the end I'm going to show you the complete answer again, and the question for that matter, the complete answer again so you can get it in big picture. So you don't need to write it down twice. Oh boy. Alright, so here's a question. Now you'll notice that we are trying to find Ka, and we're given pH. Now we know that pH tells us something about the concentration, so this is the kind where I'm told at equilibrium the concentration is such. So write down a reaction. Now I don't know the formula for propionic acid. Actually I do, propanoic acid rather, but it doesn't really matter. We don't need the formula, we need to know it's a weak acid. So it's going to be a proton donor, and there it donates a proton. Ice table. Okay, so as the acid dissociates, some of this disappears and I increase the concentration of hydronium and propanoic ion. So at equilibrium I have those concentrations. Those are the concentrations that are important. But I also know that at equilibrium the pH is 2.78, which means I can have a way to calculate one of the equilibrium concentrations. And if I have a way to calculate one of the equilibrium concentrations, that means I can calculate the other equilibrium concentrations. And once I know all the equilibrium concentrations, then I go to my equilibrium expression, my K value, or the K expression, and then I can put those values in, solve for K. In this case I'm labeling it Ka because it's the equilibrium constant for a weak acid, and I end up with my K value of 5.7 times 10 to the exponent negative 5. Okay, so again, I'm going to show you the full answer again, but all in one page, so it's going to be a little bit more compact and hopefully not more cluttered, but then you get a bit of a big picture look at it. So there's the question again, same ones you had before, please don't write it down again. You have your ice table. You use the pH information from the question to solve for X, one of the equilibrium concentrations. You use that to calculate the other equilibrium concentrations, and then you substitute those into the K expression to find the K value. That's all there is to it. And we did a few of those before. Actually, we did a lot of those in the other kind of general equilibrium, because it was really easy for me to tell you, here's an equilibrium concentration. The other kind of question was, if you were given the value of K, then use that to find the equilibrium concentrations. You'd also need to have the initial concentration. For us, for a weak acid, that's determining or calculating or predicting the pH. So here's a kind of question. Same thing, I'm going to go through the full question, then I'll give you the full answer rather, then I'll give it in a snapshot. Okay, so that's our initial concentration and our K value. The reaction is going to be acetic acid. I don't know the formula. Again, you probably do know the formula, but we can shorten it up. And what some people do is they'll just write these things as HA as our generic weak acid. And that's fine. All we really want to do is get a bit of an expression so we can follow what's going on. Our ice table. Okay, so we start out with acetic acid and none of the other. Some of that is lost and dissociates into hydronium and acetate. So at equilibrium we have these concentrations. Now what we don't have is a pH. We're asked to find that. So I still don't know that value. So what do I have? I have the equilibrium expression and its value. Now if you think back to when we were doing this before, they were always set up to be easily solvable. Well, what can we do? We're going to substitute and solve for x. We're going to try and do the same thing. Here we're going to run into a bit of a problem though. So that's the thing again. I put my x's in and it comes to this. Now mathematically we have two options. And we're going to take a quick look at one and a long look at the other. So just so you're aware of that, our option one is quadratic formula. Now if you've done a lot of math and you've done a lot of quadratic formula, you might be thinking that that's the easiest, most sensible, most obvious option. And if that's the one you want to use, it's perfectly fine with me. Our other option is something called successive approximations. And all I can tell you about successive approximations right now is that it looks weird at the beginning, but once you're used to it and you know how it works, it actually goes along quite smoothly. And you've probably heard me say that a lot, that it looks weird, but it actually gets better. We'll go through that one slowly, and unfortunately that means this thing gets a whole lot longer. But once you understand how it works, it actually works pretty smooth. So quickly on the quadratic formula, in case you choose to use it, you need to isolate x or get it all the terms on one side, so you can get your a, b, and c values. So all setting equal to 0. You're going to multiply this through to the other two. So you end up, in this case, 1.8 times 10 exponent negative 6 minus 1.8 times 10 exponent negative 5 times x. Bringing everything to one side, setting equal to 0. Then I have my value of a, b, c, which I'm going to pop into the quadratic formula, and I'll get rid of that. And there's my values. Now when you do this, if you do this, and you don't have to for this question, when you do this, if you do that, you'll get two answers. You'll always have two roots. Well, in this case you'll get two roots. One of them will be negative, and because we're talking about concentrations, x is supposed to be a concentration, the negative root doesn't make sense, so you only look at the positive root. Okay, so if you like that method, go for it. Other option is successive approximations, and this one has a real history. This is back before people had calculators easy to go and all that other stuff, and they didn't like doing math by hand, so we had a way to, estimate. We start out kind of the same way, but now here's where we go a little bit different. We take the square root of both sides, so now I have a statement that's x equals something. My next line, my next thought, is that x is going to be quite small. In other words, I'm going to ignore, assume that that x under the square root sign is small enough that it won't matter. And then I'm going to test that assumption. So it's kind of a guess and check, and I'm just going to guess and check my way through until I've guessed correctly. It's not random guessing though, it's very systematic guessing. So then this statement becomes that. So I've ignored the first x, ignored the x under the square root sign, and I come up with a calculation for the other x of 1.342 times 10 to the exponent negative 3. Not 0, but pretty small. Now what I want to do is I want to check that answer. I want to check to see if that guess approximation was valid. If it's valid, I put it in and I get my answer back. So what I do is I assume that this value for x, I put it into the x under the square root sign. So my question, or my calculation, becomes this. So now I'm doing 0.1 subtract that, and I multiply it out and do the square root, and I get 1.33 times 10 to the exponent negative 3. And I want to draw your attention to something. It's not really different, but it's a bit different. So 1.33 compared to 1.342. Now, it's close, but not quite. So what I'm going to do is I'm going to do that again. I'm going to take this and put it in for x. Okay, so in other words, going back to here, the last thing I had, I put it in, so that's the same x2 I got. My second approximation for x, I assume now that x is 1.33 times 10 to the exponent negative 3. Put it in for that 0.1 minus x. And then I do the calculation again, And I end up with, hey, check it out, 1.33 times 10 exponent negative 3. In other words, my second guess of a value for x was correct, or at least, to the third decimal place was correct. So that when I check it, I get that answer back. Both x's agree. Since x has stopped changing, I take that to be the correct value. Now, I want to tell you what happens. If x is here, whatever that number happens to be, x1 is going to be too high, x2 will be too low, x3 will be a little bit too high, x4 will be, but it's going to keep moving in and getting closer and closer to the correct value all the time. The number of trials you have to do, the number of approximations or cycles, I'm going to use the phrase, the number of times you have to go through that will depend on how good your first assumption was. If it's a very weak acid, then assuming that it's pretty much nothing, your first x, that's a pretty good guess. Okay, so once I know x, I'm not done yet. That works in math, but not here. X, don't forget, was my concentration of hydronium, and I use concentration of hydronium to find pH. Okay, so again, full question in a lot of detail. Let's go back and have a look at it in a snapshot. There's the question again. I'm changing up my ICE table, and if you really like the ICE table, that's great. But if you notice for both of those questions where we did the ICE table, the concentration line and the equilibrium concentration, so here my F stands for, whoops, wrong one, initial concentration and final concentration. So I'm now talking about if tables rather than ICE tables, but they're really the same thing and they serve the same purpose. So then I go to here, I put my values in as I have them, I solve for x, and before you think, wow, successive approximations looks like a lot of work, most of that work could stay in the calculator. I'm only really interested in my final guess, my final correct guess for x. So I would do things like this: write down x1, write down x2, write down x3. I don't even really need to write them down other than for me to keep track of how much has it changed. Okay, now I'm happy it's going to be, it's held constant. Once I know x3, I use that to find pH, which I haven't done in this question because that's no different. So this is using successive approximations. I know it's a little bit strange and it's going to take some getting used to, and we'll do a couple in class. End of the day, it does not matter to me whether you use successive approximations or if you use the quadratic formula. Whatever you're comfortable with, whatever gets you there. And again, as I mentioned, historically, before people had graphing calculators or calculators that could do a lot of math really quickly, successive approximations made things much easier. But does it really make it easier now? Not so much. So if you like the quadratic formula and want to use it, by all means go right ahead. We'll end up with the same value of x. We'll end up with the same pH, and that's what's important. We'll try a few in class. We'll hopefully get comfortable with successive approximations if you want to give it a try. Otherwise, as long as you're comfortable, you can solve for Ka or you can solve for pH. That's where we really need to know what's going on. And then we'll do this same thing for weak bases. We'll talk to you in class. Later.